Eric Rexted, University of St. Andrews, back with the second part of the importation of data for a simulated density surface model fitting exercise. We've gone through the two steps of the data import, but we have to reconcile all of our new field names in our database in such a way that program distance knows where they are. So we're going to go to the Survey tab. We're going to go to this survey that's opened by default when you tell distance your starting project. We then look at the properties associated with that particular survey. These are all of the radio buttons that we checked when we created the new project, but behind those tabs are some more tabs that check to make sure that we have the appropriate layers in this project. So we did create a new layer called segment that lived in between the transect layer and the observation layer. We're just making sure that that's appropriate. In addition to that, we have another number of data fields. Distance expects them to carry certain names. So we double check that we have a field called area defined at the region layer. Effort, however, for density surface modeling is defined at the segment rather than at the transect layer. And so we need to tell distance that there is a field called effort in the segment layer that will relate to the effort in this survey. We didn't name our perpendicular distances per distance. We named them simply distance. And likewise, we didn't use the to-name field name for cluster size. We used the single word name for the cluster size field as size. All of these items are checked on the top of page 110 in step 5A2. We now have our database changes made. We can go back to the data field. And now we want to make one final check that all of our distance units are measured appropriately. Study area size is in square meters. Line length is in meters. Effort, however, we haven't specified the units of that, so we better specify consistent units of meters for it. And finally, the perpendicular distance has no units associated with it. We'll set it to meters as well. All right, we have all the bits and pieces together dealing with the data for this project, so we should now be in a position where we can actually try to fit a detection function. So, oops, don't close that yet. Let's go to the Analysis tab and fit a detection function. We'll build a new model definition. I won't concern myself with truncation at the moment. Remember, we have to use the MRDS mark recapture distance sampling detection function fitter. So we'll say we want half normal without adjustment terms as the detection function or the distance sampling model fitted here. I'll describe that here as well. And I will try to see if I can fit a half-normal detection function to these data. These data, by the way, were simulated from a half-normal detection function, so hopefully that works out reasonably well for us. We'll wait while distance finishes the job. It states there's no truncation distance, that's fine. We have what we wanted out of MRDS, namely a half-normal detection function. So that's fine. I'm now going to fit a new model, but now I'm on to density surface modeling. I'm going to call this a new model. I'm going to need a different analysis engine. I need the DSM analysis engine here. I'm using the DDF object created by MRDS, and the only covariates I have at my disposal are latitude and longitude. So I'll build a model for latitude. That all worked as planned. Another model. That got in my way. Let me build it from here. Sneak down here to the properties just for a second and ask to see a few more pictures of the models that I'm fitting. Clearly I mistyped, so let's try to correct my typing error. Renamed my model definition. I've redefined it. There we are. Green lights. I get some residual plots. And I also get to see the strength of the longitude effect. I'm going to fit another model. This time I'm going to use a bivariate smooth. Univariate smooths on both latitude and longitude. Interestingly, there's a fairly flat surface with wide confidence intervals for the effect of longitude, somewhat narrower confidence intervals, and a stronger relationship for the latitude covariate. Let's do one last model. This time I'm not going to do a smooth at all. I'm just going to fit a linear effect for latitude. Nothing to plot because I didn't fit. I've just fitted a linear term so that there was no plotting to be done there. So I'm going to rerun that. This time simply asking that the plotting not be done. Okay, completed analysis. There's one feature that I want to present to you, and that is changing the contents of this project browser. In this case, I want to bring up the GCV score. I want you to be able to view that here, because that's going to be our model selection tool. Point of the exercise is, because these are simulated data, we know truth, and the GCV score in this case conforms. The one with the smallest GCV score is the one that has latitude only as a predictor. Well, it just so happens that this was the true shape of our density surface. Our density surface was indeed strictly a function of latitude. So we had a density gradient in the north-south direction, but no density gradient in the east-west direction. And so in this case, the GCV model selection tool led us to the correct model. So we've now been through the steps of importing data, fitting a detection function, using that fitted detection function to aid us in fitting a density surface model. Hopefully you found that useful for your future density surface modeling exercises.